split each channel, and I forgot to record. So going back to colocalization, you have this sample, which is a neuron. You can see that there is 4 different labels on this neuron: one red, green, blue, and cyan. And the question is what? What do you want to see? Do you want to see if the green is overlapping with the red? You want to see each pair of colocalization? You want to see a combination of more than 2 colors? If you want to see the green and the red, do you want to see it everywhere in the cell, outside of the cells, in the soma, or in the dendrites? Do you want to look at the puncta, or do you want to look at the overall fluorescence? The question of colocalization is very broad and depends on the image you have. So there is not a single answer to colocalization. It really depends on what you have and what you are interested in. Some people might look at vesicles, so they want to see if this vesicle red is also a microvesicle green. Some people, they are just looking at the cell body and they just want to compare the general intensity of the fluorescence. So it really depends on the case basis. So the first thing is it's not a proof of interaction. If you want to prove an interaction, there is another microscopy technique called FRET, which is basically making fluorescence when things are in very, very close contact, such close that it is interaction. You can also do a co-immunoprecipitation, which is a more molecular biology technique to see interaction between molecules. So there is dedicated technique for doing that. But colocalization can be an argument in favor or against interaction. Colocalization is also limited by the resolution of the microscope. We saw in the precedent lecture that we are limited to 200 nanometers in X and Y resolution. So you're going to be limited by that. So you cannot say if 2 things are closer or than 200 nanometers. So that's a limitation. And there are 2 ways of looking at colocalization. The first one is looking at the proximity of things. The second way is to look at correlation of intensities. So this is 2 different approaches, and they define 2 terms to refer to that. The first one is co-occurrence. It's when you have 2 fluorophores that are within the same spatial region. The second one is correlation, and it means that there is a link between the intensity of the 2 fluorophores. And that's really 2 different aspects of colocalization. One has to be linked to the other. There is a very nice review by Tenglong Xu from the Janelia, and this is the link to understand better what is co-occurrence and colocalization. I want to give you some very practical advice for the colocalization. The first one is that the red and green, but is always used by everybody on the microscopes and on papers, is not good because it's not, it doesn't help the people that are colorblind. So you need to use magenta and cyan. And if your boss doesn't like it, you can explain that you need to include at least 10% of the people that are colorblind, and this is how you visualize in a better way co-occurrence. The second thing is that what we are looking at, it's gray, the level of grays that have been colors with red and green. And level of grays are usually better for humans to appreciate the intensities. You see that the human eye is not very good in the blue channel, for example, but it's pretty good in green and the red. So if you want to visualize in a neutral manner the intensity, put it in a gray color, and level of gray is much easier. The second thing I want you to know, it's about brightness and contrast. It modifies the way the image is displayed. And this is very important because you can actually trick the data in the way it's displayed. So in the first one, I have the auto-enhanced features on. So the brightness and contrast is adjusted based on a specific algorithm. If you reset the display, then you get this. You see that the staining is much different. You still have the puncta, but the background is very black, and the intensity is much lower, especially where here in the nucleus, in the cell body. Same thing can happen here, where you have your cells. This is a green channel. If you reset the display, then you see that actually in the middle of the cell, you don't have a lot of brightness, but you have 2 punctas, but we're completely disappearing in the middle of the saturation here. So egalization of the brightness and contrast is very important because we use this auto enhance feature to kind of adapt to the human eye capabilities. But when you want to do the analysis, you have to take this in account. Another way, if you want to compare the intensities, so you have to adjust the brightness and the contrast the same way for the two channels. But you can also put this little display, which is a calibration of the intensity. In this case, I put the display between 0 and 6,000 for both channels, green and red. And then I use the lookup table fire, which is basically showing you the intensity with a range of color. It helps you to visualize where its intensity is higher. And you can see that the green channel is actually much higher than the red channel when things are normalized and calibrated. So if you want to compare intensities, you need to put this thing here. So we know what is intensity based from. And then you can call it your red channel, or you can call it whatever proteins you are looking at. And here the other staining you are using. Then, so this was the practical tips for colocalization, just little things that you can do for improving. Then if you want to quantify the colocalization, there is two ways of doing that. The first one is based on objects. And basically what it does, it's define object within your pictures, and then it's going to calculate the distance between them. You can also calculate the kind of percentage of overlap between these objects. The second way, it's based on the intensity, and this can be done with co-occurrence or correlation. You're going to look at the variation of the intensity for the two fluorophore. So I'm going to present a bit the co-occurrence based on the object because it's very easy to do and it's reachable by a lot of people. The first thing you need to do is you have to segment your image, exactly like we did when we did the thresholding. We segment the image into objects, particles, and then we're going to identify each of them in each respective channels. Then when these objects are identified, you can either look at the center of this object, or you can look at the center that is weighted by the intensity. So where is the brightest point of the object? You can also look at surfaces that are shared or not shared, and you can measure the overlap between them. Then when you are doing co-occurrence based on objects, you look at the distance between 2 points. And if the distance is lower than the resolution of the microscope, then we say, okay, they are in the same spot because I cannot separate them with my optical resolution. And at the end, what you do is you count the number of points that are colocalized, and you divide it by the total number of points you have. So it's very simple. It works very well for things that are delimited size of like an object, like vesicles or little particles, and to be in the similar size in two channels. And you can actually associate them with a randomized technique. You can have a statistical approach, but I won't talk too much about it. It's an example of image you can find in the image. It's called confocal series. It was provided by Joel Sheffield. When you do a colocalization based on the intensity, you're going to start exactly the same way than for object. So you're going to threshold your image, and then you're going to measure what is shared and what is not shared. So in this image, I did that, and I did the colocalization on the cyan channel, and I got this white area. I did that also in the pink and magenta channel, and I got this area. So it's overlapping a tiny bit here between the two, but also here outside. And then you can actually measure what is the area of each of them. So I have 84 microns square for the magenta and 86 for the cyan. And you can measure also what is shared between the two, so this area here. You can make a ratio between the two, but you can also weight them by the intensity each of them. And this was done by Eric Menders in 1993. So it's not too long ago that he made this technique. It made two different coefficients. One is called the MOC, Menders overlapping coefficient, where it varies between 0 and 1, and it tells you the percentage of pixels that colocalize above the threshold of the other. So in this case, we will have 3 square microns divided by 86, and we will give you the percentage that is overlapping. It also defines some specific overlapping coefficients called M1 and M2 for each respective channel. And this gives you for each channel what is the percentage overlapping over what is the total size of the channel. So yeah, that's a technique from Menders. It's very easy to implement, but it's very sensitive to noise. So you have to define ROIs, and you have to kind of remove everything that is outside your region of interest. There is a plugin to do that. It's called Colocalisation Finder. I found it very easy, and we're going to go back to Séance to look at that. So I'm going to close this up. I'm going to get my images that are on my desktop, and they are in the data folder, and they are called image samples, and it's called the confocal series. So that's my confocal series. It's a Z stack again. It's in green and red, and I'm going to do the maximum intensity projection to simplify things there. So this is my image. So now I'm going to go to plugin. Colocalisation Finder is already installed here. And what this plugin is doing, it's showing you a scatter plot of the image. So this is a very useful thing. Obviously, it doesn't work. And why does it work? Confocal series, max confocal series, there. So in this scatter plot, what you have, what you should see and you don't see here, it's little pixels everywhere here. Ah, yeah, c'est ça. Il fallait split channel. Split channel. There you go. I'm going to start the plugin again. Oops. So you have to define which image you are looking at, and then you have to click OK. Now you have this. So this is a scatter plot. It's showing you the intensity of the green channel here versus the intensity of the other channel here. And he put every pixel where it should be. So you can actually zoom in. Oops. And you can also adjust the brightness. Oops. If you want to see more pixel or not. So if it's very white, it means it's a lot of pixels. This is our very low pixel intensity in the green channel, and it gets higher as you go to the right, and it goes higher for the red channel as you go to the up. So what I'm interested in, it's pixel that colocalize, and what you can do is actually take this rectangle here and move it away. And when you do that, oops. And when you do that, it's supposed to change the area colocalized here, which it doesn't do for a reason that I don't understand. Let's try again. There you go. So now you can actually move this square until you see where is the area colocalized. So obviously you are interested in pixels that are very green and very red. So you can actually select the amount of greenness and redness you want to include. So you see, for example, here, this is the only part where things are overlapping. If I go a bit higher, then I'm going to get pixels that are dimmer in the green channel, but still in the red channel. So this is a very easy way to kind of visualize where you can colocalize. And at the same time, it gives you kind of the coefficient you're interested in. So if you click set, I'm going to select overlap coefficient, which is the Menders coefficient. I'm going to select also M1 and M2. So as you move it, it tells you what are these coefficients in the real time. So it tells you that the overlap here is 60%. It's okay. It's because I kind of crop into this area where I know I have overlap. If I take the full image, you see that it goes down to 17%. It's because there is no overlap, or the pixels are very weak in the other region. So you can use that as a mean to find where is the overlapping image. Again, this is just a proxy to kind of find this information quickly. Obviously, it's a Z-stack that has been flattened. So it's possible that what we see as a colocalization is actually in two different planes. You can actually check this into the original image that is here. Where is that? Is there? So you want to make sure that the red appears at the same time than the green, but it seems that actually the red is above here and below the green. So when you flatten it, you lose this information. So it's likely that the colocalization in this case is not true. There is no colocalization between the green and the red. So be careful when you flatten your image. Okay, going back to presentation now. So this was kind of the exercise I planned to kind of discuss colocalization finder and the values you can observe and discuss it. But because of the lack of time, we will not go into this kind of detail today. Second thing, I wanted to use this plugin called Just Another Colocalization plugin. It's been installed also in the Sense environment, and we can actually have a quick try at it. So if you go to plugin and Jacob, and when you open this, it shows you a new window, and it also puts the two pictures side by side. You can choose what coefficient you want to analyze. For example, I told you about object-based method. So when you select that, it brings you to these object tabs, and it tells you it asks you for parameters. What is the size of the particle you want to look at? In my case, maybe they are 10 pixels big. You're gonna say show colocalization table only, for example. You can also put a threshold to threshold your image. So this is automatically calculated, but you can actually modify it if you think it's not good. And then you can click analyze, and it shows you each particle that has been detected. Also shows you if there is colocalization and how much of them. In this case, there is no colocalization particle. So yeah, because probably the size is too small. If I put a higher size, but then it will include this guy and it will overlap. You can also use this for plotting the scatter plot, very useful tool. I found it buggy. So there is, for example, here, you cannot see the things because they are in white over white. So if you want, you have to kind of select and then see your, maybe the first one I don't want to see it, but the second one I want to see it. And the third one. So I found it buggy and not very good for the scatter plot, but this is a tool that's supposed to be working. You can also calculate the Mendel's coefficient using a threshold. If you do that, you click analyze, and it's going to show you in the log what is the Mendel's coefficient for the full image and also for the thresholded image. It also calculates the overlap of the two. So this is actually a very nice tool, and there is an article that tells you everything you need to know about it. You just need to click there to get the article. All right, I'm going to move next to an important thing is how do you test that what you are measuring is good or not? For example, in this image, you have a Mendel's overlapping coefficient of 0.9, showing that the two dots are really overlapping to each other. If you take the green and you scramble the same pixel, so you move the dot around in a randomized fashion, you can also use that and recalculate the MOC. And if you do that, then you see that your MOC is 0.1. So if you do that a certain number of times, you can build statistics on this. And this is done with Jacob, which is has a randomizer included in it. If you do a lot of randomization, you can have the distribution of the MOC. And you see that if you look at the randomized version, you have a maximum at 10% colocalization. In your case, you are here at 0.9, which means it's actually a very, very good overlap. because it cannot happen in the random fashion. If your dots are overlapping that much, it's because they are close to each other. This is another example where you have the same mock as 0.9. You scramble the same image like that. So you scramble the green image, but you don't touch the red. And you have also a mock of 0.9. And if you plot this, you see that doesn't matter how much you scramble things, you have so much pixels or so many pixels, everybody is positive. So is your overlap significant? Well, not really, because if you scramble everything, you get the same result. So in this particular region, you will always have overlap because everything is green and red. You basically have no black area to move things out. So this is how you statistically test for significance, and the Jacob software gives you the p-value of these things. And this is what I planned as an exercise for testing that. This is the example of what I've done, so you don't have to do the exercise yourself. So you have the original colocalization. You scramble the green, you don't touch the red, and you calculate the Mendel's coefficient. In this case, you see that I have a Mendel's coefficient of 0.17, meaning that they are avoiding each other. If I was scrambling things, I would have a Mendel's coefficient of 0, meaning that it will, in this case, in my image, they are separate. So I can show that my data is actually not overlapping. So it's statistically significant that they are avoiding each other. So we saw colocalization. I talked about co-occurrence most of the time here in two ways. One was object-based, the other one was intensity-based. The most important thing is that you can also look at the correlation, which is the link between the intensities. And this relationship can be positive or negative between the two channels. We really link the value of each pixel to the other one. So if you have a channel that a pixel that increase in one side, the other one must increase or decrease, and this can be predicted by a coefficient. So you can also use a scatter plot or a 2D histogram to kind of visualize this. And this there is two people that worked on this coefficient. They are called the Pearson coefficient, but it actually was made by Francis Galton much earlier. You see that this kind of pretty old techniques. So they define the Pearson coefficient, which look at the values of intensity, and they compare it to the mean intensity of the image. So if you have pixels that are far from the mean, they will be have a stronger impact on the value. And also the Pearson coefficient look at linear interaction. So if you have a perfect line, if your points are perfectly aligned, then you will have a coefficient of 1 if it increase, or -1 if it decrease. It doesn't matter the angle of the line. If things are more spread out, the coefficient will get closer and closer to 0. And when you have a very scattered plot, then you have a coefficient of 0, meaning they are not correlated. There's another way to look at correlation is using the Spearman coefficient. This was made by Charles Spearman at about the same time. Instead of looking at the intensity, is going to rank intensity. So this, you're my highest intensity, I'm going to give you 1. This is the second highest, I'm going to give you 2. So you do this in both channels, and you look at the correlation between this rank instead of looking at the correlation between the intensity itself. And this is very useful because you can look at a non-linear correlation. And the Spearman coefficient in this graph is equal to 1. So you have a perfect correlation, non-linear, but the Pearson coefficient is only 0.8. So the bottom line is that the Spearman coefficient that gives a different approach for things that are non-linear. And often in biology, when you have interaction between two proteins and they get in close contact or in close vicinity, you have non-linear interaction. So allosteric and things like that are non-linear. So maybe the Spearman will be more appropriate. So how do you work on colocalization? There is a lot of aspects that are related to how you take images and to the microscope. This is very too long to talk about today, so I didn't put the emphasis on this, but there is a very nice article that can give you all the pitfalls and the things to avoid when you are doing experiment for colocalization. I suggest to start with the Pearson coefficient because it's very easy to get as a number. So you use the Pearson coefficient first and look for values that are higher than 0.5 because a coefficient low has little meaning. So if you have a higher than 0.5, then you can look deeper into the analysis. Always perform the randomization of the image so you can obtain the p-values. And this is very important to get statistics out of your colocalization. If you have a structure that is well-defined in space, such as vesicles or puncta, then object-based colocalization is simpler to use, and both of them are valid. So you don't need to do all of the techniques. You can do one, but it's good to check with other techniques if the results are similar or different and to publish them. I found this in this article. It's a kind of a guideline to how do you quantify colocalization. You can see that there is no one single way, and when you go in one way, you can get redirected into the other way. And this gives you a kind of outline of how you can do your quantification. These are all the things you should check when you are doing a quantitative analysis, and I didn't want to go into the details of that because I think it's too long for today, so I put this on the side. And then I put an exercise because I think it's important you learn to do statistics in using a tool that is powerful and easy to manipulate data and make graphics. So I wrote some exercise to do in R. And because the interface on the Séance is really the raw R, it might be useful to do it on my personal laptop. So I might use this to do the exercise example. So I'm going to switch here, stop sharing, and move to my personal laptop. So in this data, I have these things that we call the overall measurement. And also I have all this measurement here, but we made for each particle and for each slide. So I'm going to put them on my desktop. I'm going to use something we call R. So R is a statistic and programming language. You can use it using the raw interface of R, which is, it looks like that. Or you can use R Studio, which is a more user-friendly interface. So this is the R, and you can write something and it will do things as you write them. But the console is very limited and doesn't have a lot of options. So there is another software that is using R below, but it gives you a nice view and a nice environment to kind of work with that. So I wrote some scripts to kind of process the data we have here, we have generated, and I'm going to load these scripts and we're going to go through them. We're going to go through them if I find my scripts. There. Okay. So the first script we are using here, it's something to read data that is located in this file. Oops, in this file here. So here it's actually I don't need the Excel table. I need the result CSV table. There you go. So the first thing you want to do is define where you're going to save everything. And in this case, you're going to create an object called output. This arrow defines your object, and this tells you it's actually a string of character. So you can run a line just by selecting the line and clicking run. When you do that, it tells you that output, it's now in your value, it's a variable, and it's defined by this. You have also, you can select a file by clicking this function, file chooser, So I'm going to click that, and it should show me a window, and then I can select my file that I'm interested in, which is cell and fossil results. So now I have my file, but the file is not read yet. So I have to read the file, and there is a read CSV. So I'm going to read the CSV file. So now I have a data file. It's called data. If I click data, it's going to display all my data. A useful function is to actually go and look at the structure of the data. So structure str, and you look at data, and it tells you for each column what is the data that you have here. So I have a first column, which is just numbers. Then I have the labels, and then I have the numbers here. There is a bit of a manipulation of things to do. I don't want to give you the detail, but basically what I'm interested in is having this name in a separate column. And what I did is I split the name just to have control and test into a specific column. So you can do that using these 3 different functions. So I created a new column called file name, and I put a part of the file name inside. I created a new column called channel, and I put the channel in this column, and also created a group so I can separate my data based on the group. And you can see that if I display in this data, the group, I have only control and test. And this is going to help me to kind of separate my data. R is very good for making graphs. And I'm going to show you how to make a graph and why it's important to make graph quickly and easily. I'm going to do that now. I made a loop because I want to create all the graphs for all the measurements and for all the channels. So if you want to run that on that, you can. The first thing you need to do is when you have data, it's to kind of segment your data. So I made 2 separate tables, one for the control, one for the test. And this is how you make it. I won't go into the detail because I want to focus on the most important thing, which is plotting the data. Sorry. In the end, you will have to you can run everything. You can run everything in one go. In this case, I just want to show you what we can do. So I want to plot boxes because I have a lot of data, and I think box plots are pretty good to show you data and how the data is split. So missing this line. So you run this line, and it's showing you basically just making the graph itself. I can tell you what has been written. You look at the mean, standard deviation, and the confidence interval. It doesn't show you all the points. It shows you only the outliers that are outside of the points, so you can have a good idea of what the data looks like. And this was made using just one single line, which is box plot the data of this specific mean of channel 1, and separating the groups control and test. So here I have a very easy view of what are the data, and I can do this in a batch. Also, I put here the mean of the control, so I know exactly what is this value. And also you can calculate the t-test very easily in R. The t-test function is actually just there. Stat results. So the function is t-test, and you put your control and your test data, and that's it. It gives you the stats result. So you see that here I have a p-value of 0.01. So it's almost significant because I have a lot of points. The question I'm asking is this increase in intensity real, or is it meaningful? This is something that biologically we need to answer. Obviously, plotting one graph is not very interesting. So I made this kind of loop where we're going to plot all the graph for all the channels for all the values. And this is very easily done by clicking run here on this loop. And now we generated all the graphs. And so I can just look at them and decide, oh, actually here there is a p-value of 0. So it's very different. I have some outliers here, but you see that it's in the SKU of channel 1. SKU is a measure of kind of the surface of the particles. So it's very different. I can look into more details into this. I can also parse the data and look at the p-value. Here it's not significant. So this is the mode, how the intensity are spread into your channels or into your particles. And this is the mean intensity, and so on and so on. So this is a very easy way to look at data. But remember that this data comes from the full image mean. So we look at the full image. We don't look at individual cells. So we have a good idea of what's going on, but it's not really refined to a specific cells. In this case, you see that this is the maximum intensity. You see that some of the images, you have 3 images and 2 images that have pixels almost at the limit of the camera. So maybe this I can actually crop out what these images, or I can look at them at least to correct if they are good or bad. So that's what the first script. It's pretty straightforward. You load your CSV, you play a bit with it, and then you say, okay, plot, make the graph for all the channels and so on. So the semantic is kind of easy to do. The only thing is a bit difficult here is that if you want to save a graph as a PDF, you have to kind of open the graph first. And that's what this function does. It's open a PDF, plot the PDF, and close it, basically save the PDF. If you don't open and close before plotting the graph, it will actually display the graph for you, but you have the option to save it. So was the first exercise for R, and that's the result you get from it. The second one I want to show you. It's related to. So I made a second script, and you will have this script. I will give them to you so you can play around with the data. It's because we generated, if you don't remember, this folder with a lot of images, but also all the measurements for each particle. So I'm going to open one of the CSV files so you can have an idea of what the data look like. But I have a lot of them. So I need to kind of open them, but also merge them one by one. And I wrote a small function for that. And it's clearly not hard because I'm not a good programming guy. But what I want is, instead of looking at one data point per image, I want to look at each individual cells and get all the data. And this is more relevant in science. So the script I wrote is exactly the same. So define an output. Actually, I'm going to clean my environment here. Define an output, which is the same. It's going to be saved into my output folder here. And then I get the list of files, and I put them here in something called input. You can see that it looks at the full path, and the pattern is only taking the CSV file. Actually, there it's a mistake. So the only thing I need to do is put my file into the input. Oh, they are already there. So I'm going to run this command. So now I should have a list of files. I'm going to run this variable. And here I have my list of files with all the CSV files one by one. So I'm going to run through this list and read each of them and put them this into a data variable. And then I'm going to create something called big data that's going to gather or bind the rows of each file. And if you do that, it's super fast. And now instead of having just a single data, I have a big data. And if you look at that, you have this with the label, but you have all the data points until the end. So I have my big data. Now I can actually play a bit with it the same way I played with it before. I am making groups and things like that because it's going to be easier. You can also save it. And this is a very useful function. So I'm going to save it into my output as a CSV file. So it's there. And you can open it with Excel if you want. Some people prefer Excel for manipulation, but In this case, gathering all the file would have costed me a copy and paste 50 times with possible mistakes. It took me 5 lines, and there is no mistake in that. So now I want to graph the same way I graphed for the previous things. I want to graph exactly the same thing for the big data. And this is done by running almost exactly the same function. So if you do that, then it's going to run and create all of these graphs, but is comparing not each image, but each particle itself. So now the p-value is going to be very close to 0 because we have 60,000 data points. One of the value we can look at is maybe the mean intensity of channel 1. And you can see that there is no difference between the mean intensity of channel 1 for the control and for the test. If you look at channel 2, now I have a difference, and the p-value is 0 because I have a lot of data points. And the difference of intensity is very low. One is 1500 and the other one is 1600. And also I have a lot of outliers, meaning that the test group is more spread out than the control group. So meaning that my test is doing something on my cells. It's increasing a bit the brightness of the channel 2, but not too much. Another way to look at this, so I can scroll all of this data one by one and do the analysis, and that's what the person that generated this data should do. You can also plot a scatter plot. Yeah. The maximum, minimum, min, max. This is the maximum of channel 2 and the maximum of channel 1. So this maximum intensity per cell. Another way to plot things, and it can be cool when you have a lot of data points, is to use a scatter plot. So in this case, each point is a cell, and when there is things not moving, and you can see how the data is spreading. So in this case, we are looking at the circularity. You can ask, are my cells circular in both channels? Yes, they are, and there is no difference between the two. But you can see that some of the cells are kind of not so circular. They are very down, but most of them are between 0.9 and 1. So we could gate on them to kind of analyze better. Yeah, I could have also done the statistic on that, but it's been done already into circularity here. So the stats tells me that there is no difference. Well, at 95% there is a difference, but because we are using a very large number of data points, you should not consider this as significant. So you should at least go to 0.1 or 0.01 or 0.001. And also the difference is very limited. So I would not bet that there is a difference in the circularity. The last thing I want to do is, now we have this data. You also have the big file. You have the graph. You can do some statistics using another software called Prism. And I like it particularly because it's very user-friendly. And if you don't like stats and if you don't like programming and coding, it can be a very nice tool. So I'm going to show it to you what it looks like with the few minutes I have left. If I find the file. Oh, a result. Prism analysis. So what I have done here is I, you know, the big file I have opened before. I'm going to open it actually. So I have all my data that has been saved into a single CSV file somewhere here. Here. I want to, you know, to summarize this data, and the first thing I'm going to do is actually take everything and create a table. So things doesn't move and I cannot change anything. The second thing I want to do is create a pivot table. So if you already know how to use pivot table, you're gonna hear about it again. If you don't know how to use it, it might save a lot of time in your life. A pivot table is basically a table that you can change the columns and the rows manually. So for example, in this column, what I want is I want to know for each file So I take file name and I put it in the rows. So each file are here. I want to know the numbers of cells. So I want to know the number of cells that are being counted for each file. So I take any kind of variable here and I click here and I'm going to say I want to count. And then maybe I want to separate by the groups. So I'm going to put the groups here. So now I have my control and my test side by side. My controls are here. This is the number of cells that have been counted for each image. And what I can do is I can do statistics on that. So I copy this and I go into my favorite software, Prism, and I plot this data side by side. Using this, you can actually do very easy statistics easily with the Analyze button. So if you do Analyze, you're going to say, OK, I want to do a t-test comparing the two. I'm going to click OK. Because they're not matched, so it's unpaired t-test. I don't know if it's parametric or not, so this I'm going to leave it yes for now, but we should come back on that, especially when you are playing with larger number of data. And I'm going to also do descriptive statistics, and I want to do, no, that's OK. I'm going to click OK. So now you have the result of the statistics saying that, yeah, it's significant, and the p-value is 0.03. And you have the difference of the mean here. The mean is 73 cells for the control and 84 cells per image for the second one. You can actually plot this into a graph here. And you can bring the p-value automatically inside here. You see that I have an outlier here. So I might actually remove this outlier because it's clearly out. It's kind of easy to remove it. You can just go into the data and the outlier is here. It's the one with 140. And I'm just going to press Command E and you see that you exclude the data. And the good thing is that everything is kind of updated in live. So the t-test is updated and the graph is updated. So now you see I remove the outlier and it becomes non-significant and the p-value has changed and the graph has changed as well. So there is a slight higher number of cells in my test situation, but it's not significant because of the number of images I've analyzed. You can only remove one outlier per, and it has to be quite far. So visually, it was easy to find. Yes, so you can actually look for outliers automatically if you go to Analyze, and I don't remember where identify outliers. And you can say which coefficient. I'm going to keep the default, and then it says, oh, how many outliers do you have? In this case, it tells me I have no outliers, but in my view, or maybe the statistics was kind of high, but in my view, there is a clear outlier. Doesn't really matter because at the end of the day, even if it's significant, I consider it as non-significant because of the number of cells I've counted. The second thing I can look at is the size of the cells. So this is defined by the area. So I did exactly the same thing. I go to my Excel file, which is here. And instead of looking at the count of the area, I'm going to select the average of the area. So this is the average per image. But what I want is not the average per image. I want the area of each particle itself. And this I can find it if I put label here instead of file name. So if I put label for each image, for each ROI or each cell, and for each channel, I have my area in the control. And down below, there is the test. You can see that there is channel 1 and channel 2. So there is a duplicate because the area is the same. So I need to kind of put a filter for the channel. You're going to go to channel here. And you're going to say, you drop it into the filter region and going to say, OK, I'm going to look at filter 1 because it's always the same thing. Anyway, it's just duplicate. So now we're going to copy all of that. and go to your prism, and you can plot it, and you have the size of the cells for each single cell, and so you have a lot of cells. You can actually plot that and do a test on this. So if you plot that now, you have a lot of points, so many that you cannot actually see them. You can calculate the p-value the same way, and you can say, okay, are the cells different in size? In this case, we know they are about the same size, about 6 micrometers square. You can look at different things. You can also look at the perimeter of cells. And now I'm gonna the principle is always the same. I'm just gonna go to the graph directly. So you can look at the perimeters, and you see that the perimeter is slightly different between the test and the control. But for me, because I have a lot of points, I put my threshold much higher than 95%. This is an indication that there might be a difference, but for me, it's not a conclusive value. You can look at the circularity, and same thing. So the perimeter is changed, but the circularity is also slightly different. Here is the test showing this. You can also look at the mean intensity, and there is no difference in the channel 1, and I don't remember for the channel 2. And there is a high difference for the channel 2. So now we are getting to find something that is interesting, because the p-value is very, very low. So now in this, I would believe this, but the intensity in my test condition for channel 2 only is different. So I have brighter pixels in my second condition than in my control condition. So this is a result that is worth analyzing in more details. And now you know where to look at. It's going to be easier because you're going to narrow down into things that are interesting. Obviously, all of that, you can do it with R. It just, depending on the amount of data, is just easier. And also, if you are fluent in coding, it might be easier to use Prism than another software. So in this case, that's how I would do it. I would use Excel. I would use a pivot table, and then I will do my stat on the Prism by bringing all the data I'm interested in. I think I look also at the average size per image. So this gives you, if within my image, there is an artifact of analysis. And in this case, you can look at the distribution. If the average each cell is way behind, you can say, okay, there is something specific about this image that I might be bad, and I can take it out. You can see also that in the way of all of this analysis are tracked. I can go back to a specific image. For example, this value of 0.8, I can actually find which image give me this value. So tracing and making your data consistent and reproducible is the main aim of doing this kind of analysis, of image analysis. So for now, we will discuss it at the next session, which will be dedicated to writing making figures, writing articles. They ask you to kind of just make the figure, and sometimes they ask you to provide the data, but this is not sufficient. You really need to track your data and how the data has been processed. And if someone wants to reproduce your experiment, they should be able to do that with all the information you give. So if I want to know where is this value coming from, I should be able to go back and find it. And this is how we do this kind of analysis. So for example, I want to find out which image is 150 here. There is 150 cells in this image. Maybe I should check the segmentation of this image. So I'm going to go back to my Excel file. I'm going to plot the counts of the area. And I'm going to put file name. And I'm going to try to find, you see, this is the test image 14. So I'm going to go back to my files and open up test image 14 with my favorite software, ImageJ. And we're going to check if segmentation was proper or if it was just like a lot of cells in this image. So that's the original image. And that's the cell mask. So why I have 140 and I don't have that many cells in the other one? Well, I guess I just have many cells here. And maybe there is some mistake somewhere too. Yeah, there is some mistake somewhere because you see that the array do not match unless I open the wrong array. Yeah, test image 14. You see that something is wrong. I am not in the good place. And these things doesn't match. So there is an issue somewhere and I have to check this and why it doesn't match. So I will get back on that and I will fix whatever was wrong and get back. So a very good way to kind of analyze, and maybe I should be more careful when I do my analysis. Why it works for one image but doesn't work for the other one. Let's try that. Oh no, I know what I did. Yeah, that works perfectly. Oops. Let's go back to test 14, which is the one making issue and the issue. Test 14. There you go. Yeah, in this case, there is an issue somewhere. So I will try to solve that, and I will see you next week for the one who wants to write something good. Merci à vous.